Alexander Fleming was born on August 6, 1881, in Lochfield, a remote farm in East Ayrshire, Scotland. He was the third of 4 children born to Hugh Fleming, a farmer, and his second wife, Grace Sterling Morton. The Fleming family lived a modest rural life, with young Alexander spending his early years exploring the Scottish countryside, developing an appreciation for nature that would later influence his scientific observations and keen eye for detail. When his father died in 1888, leaving the family in difficult financial circumstances, Fleming's mother, Grace, was determined to provide her children with education, despite their reduced means. Alexander attended Loudon Moor School and later Darvel School, where he demonstrated academic promise and natural curiosity about the world around him. At age 13, Fleming moved to London to live with his older brother Tom, who had established himself as an optician. This move proved pivotal in shaping Fleming's future prospects. He attended the Regent Street Polytechnic, now the University of Westminster, and worked as a shipping clerk at a company in Leadenhall Street. However, his prospects changed dramatically when he inherited $250 from an uncle, providing him with the financial means to pursue higher education. In 1901, he enrolled at St. Mary's Hospital Medical School in Paddington, London, where he would spend the majority of his career. Fleming proved to be an exceptional student who won numerous prizes and scholarships throughout his medical education, demonstrating both intellectual ability and dedication to his studies. Fleming qualified as a doctor in 1906, earning his Bachelor of Medicine and Bachelor of Surgery degrees with distinction and becoming a member of the Royal College of Surgeons. His academic excellence earned him a scholarship to continue his studies, and he obtained his Bachelor of Science degree with gold medal in 1908. Despite initial interest in surgery, he was persuaded to join the inoculation department at St. Mary's Hospital by Almroth Wright, a pioneering bacteriologist and immunologist who recognized Fleming's potential. Wright's department was at the forefront of bacteriological research and vaccine development, investigating the body's natural defenses against infection. Under Wright's mentorship, Fleming began his lifelong work with bacteria and immune responses, developing expertise in growing bacterial cultures and studying their behavior under various conditions. His meticulous nature and keen observational skills made him ideally suited for bacteriological work. During this early period, Fleming also served as a captain in the London Scottish Regiment, a territorial army unit, which would prove significant during World War I. He was known among his colleagues for his dry wit, love of practical jokes, and passion for golf and shooting, maintaining a playful approach to life that often surprised those who knew him only professionally. When World War I broke out, Fleming's military background led to his immediate deployment to France as a captain in the Royal Army Medical Corps, serving in military hospitals treating wounded soldiers. He witnessed firsthand how bacterial infections killed many soldiers who survived their initial injuries, as effective antibacterial treatments were virtually non-existent. He observed that antiseptics, while useful for cleaning wounds, often caused more tissue damage than the bacteria they were meant to eliminate, leading him to envision treatments that could selectively target harmful bacteria. This wartime experience profoundly influenced his subsequent research focus on finding substances that could combat bacterial infections without harming patients. Fleming gained valuable experience in battlefield medicine and developed a deep understanding of wound infection patterns, noting correlations between environmental factors and infection rates. Returning to St. Mary's Hospital in 1918, Fleming resumed his research with renewed purpose and a clear agenda focused on discovering natural antibacterial substances. In 1915, he had married Sally McElroy, a nurse he had met at St. Mary's Hospital, and their marriage provided stability and support for his demanding research schedule. Fleming's post-war research focused on several areas, including vaccine development for typhoid fever and investigation of various antiseptics and their effects on bacterial strains. His methodical approach involved testing thousands of combinations of substances and bacterial cultures, carefully documenting results and looking for patterns. In 1922, he made his first significant discovery when he identified lysozyme, a natural antibacterial enzyme found in tears, saliva, and other body secretions. This occurred when Fleming, suffering from a cold, allowed nasal mucus to fall onto a bacterial culture plate, and observed that surrounding bacteria had been killed. The lysozyme discovery demonstrated that the human body possessed natural antibacterial defenses that could be isolated and studied. While lysozyme proved too weak for treating serious infections, it validated Fleming's belief that natural substances could provide effective antibacterial treatments and established his reputation as a serious researcher in the scientific community. September 1928 marked one of the most significant moments in medical history, though its importance would not be fully recognized for more than a decade. Fleming was conducting research on Staphylococcus bacteria in his basement laboratory at St. Mary's Hospital, growing cultures in Petri dishes under conditions that were far from ideal for sterile bacteriological work. The famous discovery occurred when Fleming returned from a brief holiday to find that one of his bacterial culture plates had become contaminated with a mold. Rather than immediately discarding the contaminated plate, his keen observational skills and scientific curiosity led him to examine it more closely. He observed that the bacteria around the mold had been killed, creating a clear zone where no bacterial growth occurred, suggesting the mold was producing some substance with powerful antibacterial properties. Fleming isolated the mold and identified it as belonging to the Penicillium genus, specifically Penicillium notatum. He began a systematic investigation of the mold's properties, growing pure cultures and testing its effects on various bacterial strains. His experiments revealed that the mold produced a substance that was highly effective against gram-positive bacteria, including Staphylococcus, Streptococcus, and Pneumococcus. Fleming named this revolutionary antibacterial substance penicillin after the mold that produced it. His initial experiments showed that penicillin was remarkably effective at killing harmful bacteria while having minimal toxic effects on laboratory animals. However, he also discovered that the substance was relatively unstable and extremely difficult to purify using the techniques available at the time. In 1929, Fleming published his groundbreaking findings in the British Journal of Experimental Pathology, describing penicillin's antibacterial properties and suggesting its potential therapeutic applications. Unfortunately, the scientific community's initial response was lukewarm, with many researchers viewing penicillin as merely an interesting laboratory curiosity rather than recognizing its revolutionary potential for treating human disease. The decade following penicillin's discovery was frustrating for Fleming, as he struggled to develop the substance into practical medicine. The main obstacles were technical. Penicillin was unstable, difficult to purify, and produced in small quantities. Fleming lacked the biochemical expertise and resources to solve these problems alone. He continued his research, publishing additional papers on penicillin's properties and attempting to interest other researchers in the substance, demonstrating penicillin's effectiveness in laboratory settings and even using crude penicillin preparations to treat minor infections in colleagues and patients. During this period, Fleming was promoted to assistant director of the inoculation department and continued seeing patients in his clinical practice. His reputation as a competent researcher and clinician grew, though he remained frustrated by his inability to develop penicillin into a practical treatment. He also continued his work on lysozyme and other research projects, maintaining his methodical approach to bacteriological investigation. The situation began to change in the late 1930s when Howard Florey, an Australian pathologist, and Ernst Boris Chain, a German-born biochemist at Oxford University, became interested in Fleming's work. They had the expertise and resources needed to tackle penicillin's purification challenges. Florey and Chain began systematic research into Fleming's discovery, working to develop methods for producing pure, stable penicillin in therapeutic quantities. World War II provided the crucial catalyst for penicillin's development, as the urgent need for effective treatments motivated substantial government funding for medical research. The Oxford team, led by Florey and Chain, received significant support for their penicillin research from both British and American governments. In 1940, the Oxford researchers achieved a major breakthrough when they demonstrated that purified penicillin could cure bacterial infections in laboratory mice and humans with minimal side effects. This proved that Fleming's discovery had genuine therapeutic potential. The British and American governments invested heavily in penicillin production, establishing industrial facilities capable of producing the quantities needed for military medical use. Fleming collaborated with the Oxford team, sharing his expertise in penicillin production and bacterial testing, though he remained somewhat removed from the large-scale development efforts. By 1943, penicillin was being used extensively to treat wounded Allied soldiers, dramatically reducing deaths from bacterial infections. The substance proved especially effective against wound infections, pneumonia, and other conditions that had previously been often fatal. Fleming was elected a Fellow of the Royal Society in 1943 and continued investigating penicillin resistance in bacteria, working to understand the mechanisms by which the substance killed bacterial cells. The end of World War II brought widespread recognition of penicillin's importance and Fleming's pivotal role in its discovery. In 1945, Fleming, Florey, and Chain jointly received the Nobel Prize in Physiology or Medicine for their collaborative work on penicillin. Fleming's acceptance speech emphasized the collaborative nature of scientific discovery and the importance of careful observation in research, characteristically remaining modest about his own contributions. Fleming became an international celebrity, traveling extensively to lecture worldwide on penicillin and antibiotic research. He was awarded numerous honorary degrees and honors from universities and scientific institutions around the globe. Yet despite his fame, he remained dedicated to his research and clinical work at St. Mary's Hospital. He was appointed Professor of Bacteriology at the University of London in 1948 and became head of the Wright Fleming Institute of Microbiology at St. Mary's Hospital. During this period, Fleming continued investigating antibiotic resistance, a phenomenon he had observed early in his penicillin research. He persistently warned that bacteria could develop resistance to penicillin if the antibiotic was used improperly or incompletely, advocating for careful, targeted use of antibiotics. His prescient observations about antibiotic resistance were often ignored during the optimistic early years of the antibiotic era, though they would prove increasingly prophetic in later decades as resistance became a major medical challenge. Fleming also served as a mentor to younger researchers and continued his work on bacterial classification and identification. He believed strongly that basic research, even when it had no immediate practical applications, was essential for long-term medical progress. His own experience with penicillin, which remained a laboratory curiosity for more than a decade before becoming a life-saving medicine, perfectly illustrated this principle. Personal tragedy struck in 1949 when Sally Fleming died suddenly from a heart attack after 34 years of marriage. Fleming was devastated by the loss of his supportive partner, though he continued his professional activities with characteristic determination. In 1953, he found companionship again when he married Amalia Koutsouris-Vourekas, a Greek bacteriologist he had met during his international travels and lectures. Fleming remained interested in the broader implications of scientific discovery, recognizing that antibiotics represented a fundamental change in humanity's relationship with bacterial disease. He worried about the potential consequences of this power and took a thoughtful approach to the ethical implications of medical research, influencing a generation of scientists and physicians. Alexander Fleming died of a heart attack on March 11, 1955, at his home in London at age 73, having remained professionally active until shortly before his death. His funeral was attended by colleagues from around the world, and he was buried in St. Paul's Cathedral, an honor reserved for Britain's most distinguished citizens. Fleming's discovery of penicillin fundamentally changed the practice of medicine and saved millions of lives. Before antibiotics, bacterial infections were major causes of death, and many medical procedures were extremely dangerous due to infection risks. Penicillin and subsequent antibiotics made modern surgery, cancer chemotherapy, and organ transplantation possible by providing effective treatment for bacterial infections. The economic impact of Fleming's discovery is incalculable. Antibiotics have prevented countless deaths, reduced healthcare costs, and increased productivity by keeping people healthy. The pharmaceutical industry that developed around antibiotic production became a major economic force, employing hundreds of thousands of people worldwide. Fleming's work also contributed to fundamental advances in understanding bacterial biology and the mechanisms of drug action. Research into how penicillin kills bacteria revealed important principles of cell wall synthesis and bacterial reproduction that informed the development of additional antibiotics and other medications. Perhaps most importantly, Fleming's discovery demonstrated the importance of basic scientific research and careful observation. His willingness to investigate an apparently insignificant laboratory accident led to one of medicine's greatest advances. This example has inspired countless researchers to pay attention to unexpected results and pursue seemingly minor observations that might lead to major discoveries. The story of penicillin also illustrates the collaborative nature of scientific progress. While Fleming made the initial discovery, the transformation of penicillin into a practical medicine required the contributions of many researchers, including Florey, Chain, and numerous others. This collaborative model became the standard for major medical advances. Today, Fleming is remembered as one of history's most important medical researchers. His discovery of penicillin ranks among the most significant scientific achievements of the 20th century, fundamentally altering humanity's relationship with bacterial disease and opening the door to the modern era of antimicrobial medicine. His legacy continues to influence medical research and inspire new generations of scientists seeking to improve human health through careful observation and persistent investigation. Thanks for watching. If you enjoyed this video, please like, share, comment, and subscribe to the channel for more engaging historical content.